Hello, welcome to Science Chomp. Today we're going to be looking at absolute age dating. Now, before we continue, I'd strongly recommend that you watch the previous video on relative age dating. And in case you haven't figured it out, this is about figuring out how old rocks are. Okay, I'm just going to run through my PowerPoint, and I'm going to basically clarify things which need to be clarified. First of all, we've got a starter question over here. It says, how would you describe your father's age compared to your teacher's age? So you can either say that your father is either older or younger than your teacher. This would describe a relative age. What an absolute age is saying your father is, 50 years old and your teacher is 40 years old. That would be an absolute age. And what we're trying to do in today's lesson is figure out how old rocks are as a numerical value. Okay, so our definitions are over here. Okay, what's the difference? So relative age is how old something is in comparison to something else, and the absolute age is the actual numerical age in years of an object. Now, when we're looking at rocks, we use absolute age dating, I messed that up. When we're looking at rocks, we use radioactivity to determine the absolute age of rocks, or if we're just seeing how deep they are, of course, that would be relative age dating. Okay, so radioactivity, how does this tie in with rocks? Okay, well, we need to know what atoms and isotopes are. So an atom is like these things here. Okay, so this is an atom, and it's the smallest part of an element that has all the properties of an element. You've probably seen lots of pictures of atoms. They kind of look like these things. Okay, they've got a nucleus and an electron whizzing around outside of the nucleus. Okay, and an isotope is atoms of the same element with different numbers of neutrons. Now, this is the example that they give in the book that I'm using at school. Okay, we've got a hydrogen nucleus, and you got so this is one proton. You got one proton, one neutron, and then one proton and two neutrons. So the only way these three things differ is the amount of neutrons. Now, because it's got one proton, it's a hydrogen, because the proton number always determines the identity of the particular atom. So these are all hydrogen, but they're all different because they've got different numbers of neutrons, and that's what an isotope would be. Okay, now here's a slightly better picture. So these are three isotopes of hydrogen. You got hydrogen, deuterium, and tritium. Sometimes you call this hydrogen 3. Okay, so what's the difference? One proton here, one neutron. So the vast majority of hydrogen is like this. And if you have a look at the numbers, you got the mass number at the top and the proton number at the bottom, or the atomic number you could call it. Here we've got one proton and one neutron, so we've got two what we call nucleons, so the mass number is now 2, but the proton number is still 1. We've still got one proton. Here again we've got one proton only, and altogether we've got 3 nucleons, one proton and 2 neutrons, which is why the mass number is 3. So these are all isotopes of hydrogen. Okay, as you can see, you've got electrons, one electron whizzing around. Now, the thing about radioactivity is you have unstable atoms, and they decay to form stable atoms. So something like hydrogen 3 tritium is unstable. And what's going to happen is the nucleus is going to decay, and it's going to form something else. So let me show you what I mean by that. Okay, so let's have a look at radioactive decay in a little bit more detail. So here we have a hydrogen isotope. This is hydrogen 3, and it says here it's unstable. So what happens is it decays and it forms something called helium 3. Now, the reason why we call it helium is because one of these neutrons decays to form a proton. Okay, and if you have a look at the periodic table and you look at the element which is atomic number 2, which means it has 2 protons, it's a helium. Okay, so that's what's happening over here, and we call the one that decays, we call that the parent isotope, and the isotope that it forms, we call that the daughter isotope. And as you can see here, it's got a little definition of what radioactive decay is. It's the process by which an unstable element changes into another element that is stable. So in this case, helium-3 is more stable than hydrogen-3. Okay, we're going to look at this process in a little bit more detail right now. Okay, so here we've got a neutron. So the way you have to imagine it, it's got 2 parts to it. It's got a positive part and a negative part. The negative part, you can almost think of it as an electron stuck on to a proton kind of thing. And because you've got 1 plus and 1 minus charge, overall you don't have a charge on this thing. And what's happening is this thing, it goes away, and this is what we would call beta decay or beta radiation. And what you're left with is this electron which has gone away, and this which has now only got a positive charge, and therefore it's no longer a neutron, it's a proton. So that is what's happening over here. Okay, so a parent turning into a daughter isotope. Okay, so the other thing is, it's about half-life. Okay, if you have a look at this graph, this is where all of the atoms present in a material, these are all the parent isotope, and then when 50% of the parent isotopes decay to form daughter isotopes, so you've got the percentage up here, 50% over here, you call that the half-life. Okay, and then if you divide that by 2, you get the next half-life at 25%. Now, as you can see, what you have is now 75% have turned into daughter isotopes, and 25% remain as parent isotopes. Let me show you this half-life thing on this website over here. Okay, so if I reset this, take a note of these. So these are the parent isotopes. These are the undecayed nuclei. You got the percentage over here, and right now the percentage of undecayed nuclei is 100%. So let's see what happens when we press play. So these are turning blue, and of course this is going down and down and down, and you'll notice it never actually reaches 0. And the reason for this is that if you take a number, say for example you take 100, and you keep dividing it by 2, like divided by 2, divided by 2, divided by 2, etc., and you keep going, you actually never reach 0. So this line here never actually reaches 0 either. Here's the proof of the half-life thing. So again, I'm just dividing it by 2 all the time, and you can see very quickly the number becomes really small. But no matter how small the number gets, it never actually hits 0. You can keep on pressing the divided by 2 over and over and over again, and you're never going to hit 0. So let's have a look at the PowerPoint again. So we're starting off with the definition of half-life. An isotope's half-life is the time required for half of the parent isotopes to decay into daughter isotopes. The ratio between the numbers of parent isotopes and daughter isotopes is always changing, and that's what we saw in that graph, and that's what we see over here. So here it's 100% parent, then it's 50-50 at one half-life. Now, at your second half-life, you're going to be at 25, because 100 divided by 2 is 50, divided by 2, which is 25. So that's your second half-life. And as you can see, now you've got more daughter isotopes than you have parent isotopes. Okay, and then at the next half-life, which is 12.5% of the original parent isotope, you can see even more, okay? Now, how does all of this relate to aging? Well, we have to look at radiometric dating first. So I should say radiocarbon dating. So let's have a look at this. These are isotopes of carbon. Now we know they're carbon because 1, 2, 3, 4, 5, 6. It's got 6 protons, okay? You can count this one as well. Let's count the green ones. 1, 2, 3, 4, 5, 6. 6 protons here as well. 1, 2, 3, 4, 5, 6. 6 protons over here. So they all contain 6 protons. And atomic number 6 on the periodic table is carbon. So all of these things are carbon. Now, if you count these orange things, 1, 2, 3, 4, 5, 6, 6 again. These are neutrons. Here, 1, 2, 3, 4, 5, 6, 7. 7 neutrons. And here, 1, 2, 3, 4, 5, 6, 7, 8. 8 neutrons. So this tells us the mass. So if you add up the protons and the neutrons, it gives you the mass. And these are all isotopes of carbon. Now, I'm a carbon-based living organism, and if you're watching this, you are as well. And we've got a fixed amount of carbon in our bodies, kind of thing. If your weight is kind of constant, right? In fact, it's a little bit like this. The ratio of carbon-14 to carbon-12, so this one to that one, we can ignore the middle one for now, is 1 to 1 times 10 to the 12. So that means for every 1 times 10 to the 12 carbon-12s, we've got 1 atom of carbon-14. Now, if you're 70 kilograms, you've got this many carbon-12 atoms in your body, which is 7 with 27 zeros, so it's a huge number, okay? And then if you divide this by that, you get this number, 7 times 10 to the power of 15. So this is the amount of carbon-14 atoms a 70 kilogram human being will have in their body. Now, why is this important? Well, if you have a look at this, okay, it actually explains it all here. So if you want to pause it and read it, you're more than welcome to, but I'll just go through it with you. Here, radiocarbon forms in Earth's upper atmosphere. This is, or there is mixes with C12, which is stable. That doesn't seem to make sense. It mixes with carbon-12, which is stable. Okay, the ratio of carbon-14 to carbon-12 in the atmosphere is constant. When an organism dies, carbon-14 decays to carbon-12, so the ratio changes. Now, in simple terms, basically, we all breathe, we all eat. And so we're exchanging carbon with our environment all the time, whether it's carbon dioxide or whether it's sugar that we eat. Okay, so we've got a certain amount of carbon in our body. And if you're 70 kilograms, you should have about that much carbon-14. Now, over time, what happens is, like, if you die, you're no longer exchanging carbon with the environment. So the amount of carbon-14 in your body, it starts off at this number, and it slowly starts to decrease following this pattern over here. Okay, so you start off with 7 times 10 to the 15, and it's slowly going down. And when you've got to a point where it's 50% carbon-14 remaining, because everything is decayed and you've got way more carbon-12 now in your body than carbon-14, you know that it's 5,730 years old, because that's the half-life of carbon-14. Now, of course, 5,730 years is a long time, right? A lot of biological materials that we find, fossils and this kind of thing, they're not this old, they're a little bit younger. So what you do, if, say, for example, you had like 80% of this number, right? You go 80% up here, you'd go across, you'd go all the way down, and then it'll tell you how many years have gone by since the organism died. Okay, Now, the thing is, this is all very well with living organisms. However, if something's really, 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 really old, there isn't enough carbon-14 left to get an accurate sort of reading, right? And when it comes to things like rocks, rocks are inorganic materials, right? They never lived in the first place. And so they don't have any carbon in them. So if you're going to date a rock, and by that I mean figure out how old it is, not take it out for dinner, right? If we're going to date a rock, we have to use a different isotope, something with a much, much bigger half-life. Now, the reason why we need a bigger half-life is because rocks are so old, so very old, that if you had something like carbon-14 with a relatively short half-life, there would be such little of it left that it will be basically undetectable. Okay? So if you want to have a pause of this, have a quick read through, that would probably help you. We're just going to go right ahead and have a look at which isotopes you use and the science behind it all. Interestingly, this is only really for igneous and metamorphic rock. For sedimentary rock, it is much, much harder to date, because sedimentary rock, they're made from grains from all over the place. And as a result, you can find out how old an individual grain is, but in terms of when it was deposited to form the actual sedimentary rock, we actually can't figure that out. Okay, so anyway, we've got a rock here, we've got uranium-235, and what happens is this uranium decays into lead. Lead is Pb. The reason why it's Pb is it actually stands for the old Latin name plumbum, and that's why plumbers are called plumbers, because they used to deal with lead pipes, plumbum. Anyway, uranium turns into lead. Uranium is the parent isotope. Lead is the daughter isotope, and you end up with a graph like this. So you got the green line, which is uranium, and the grey line, which is lead. And obviously, at the beginning, you got 100% uranium, 0% lead. And eventually, as uranium decreases, obviously lead is going to increase, because uranium decays into lead. And by figuring out the ratio of the uranium to the lead, or just measuring the amount of uranium, you could say, you could figure out how old the piece of rock is. If you want to work out the half-life of uranium from this graph, all you've got to do is simply go to 50% over here, go across, and it's actually this point over here. And you go down, and you just read off the number, if there was a number down here. So it's a little bit less than 1,000 million years. It's actually in the order of around 700 million years. If you have a look at this graph, now this one's quite interesting. It's the same graph basically. You got they've got the color on here. This should be green. Okay, so you got your uranium here. You got your lead up here, and this is measured in billions of years. And this is the 50-50 point. So these bars, they represent the ratio. So at 50-50, this is the half-life of uranium. Obviously, lead is increasing. And then at the next half-life, you've got a quarter of the original parent isotope left, and 3/4 daughter isotope. So anyway, just pause it, just have a read of this, see if you can understand it. If you don't fully understand it, leave a comment below, and I'll try to explain it in a little bit more detail. But ultimately what's happening is the uranium is going down, the lead is going up, and by figuring out the ratio of parent to daughter, or uranium to lead, you can figure out how old the sample of rock is. Okay. Now, these are common radioactive isotopes that we use to figure out the age of rocks. If you're in my school, you will have to learn these and learn roughly how much the half-lives are. So best of luck with that. There's a lot to learn here. And if you have a look down here, it tells you that we need to have isotopes with a very long half-life. And the reason for that is that rocks are so old that if you had a short half-life, there wouldn't be enough of the original parent isotope left to measure it. So for that reason, you need to have a long half-life, so you have a little bit of uranium in there to measure. Okay, and we have actually figured out the age of the Earth. It's around 4.4 billion years. That's the oldest rocks that we have found on Earth, 4.4 billion years. However, we have found meteorites and bits of moon rock that are 4.54 billion years old, and we actually think the Earth is the same age as the moon and these meteorites because they would have formed around the same time based on our predictions. Okay? Thank you very much for watching. I know it's a lot to take in, but best of luck in the exams. If you want to read any of this PowerPoint, you can pause it at various stages. I'm just flicking through it now. And hopefully it all makes sense. This is a really important part. You don't need to know this detail, by the way. I gave it because, you know, it's useful to visualize. Okay, and then with rocks we figure out how much uranium we have compared to lead. Okay, thank you very much for watching. I'll see you in the next video. Best of luck in the exams. Goodbye.